joined the staff at Los Alamos National Laboratory, where he worked ever since on various topics, and most recently on Lattice QCD. But he has a wide range of interests extending far beyond theoretical physics. And we are soon going to be ready to go.
I think it is ready.
Okay, so take it.
Push the this one or this one up.
Okay. Perfect. Okay. Okay. All right. So thank you very much. We are all in a time warp when I talk about these memories of having visited the university a number of times, and I've gone through your entire, which most of you probably don't know, but your entire thing of this wonderful renovation of this building before and after, and so it's wonderful to see that the renovation has actually been extremely successful.
This is your first time back for the renovation, right?
In this building,
yeah.
In the I've been into your student center where I gave a seminar once when you were displaced there.
Oh yeah, right.
And then I think I also was in the nanotechnology building. So this is the first time back in the main. So today my goal in terms of the physics is to give you some overview of the calculations we are doing of CP violating operators and their contribution to the neutron or proton electric dipole moment. But I have been warned that almost, I don't think any of you really work on Lattice QCD. You're all formal phenomenologists, or so what's the main topics? Just phenomenology is the main area in which most of you are working in. Just so that I have some idea of what I am reaching. Okay, so most of you have, should I assume, have zero or maybe epsilon understanding of Lattice QCD?
Yes.
We don't run the programs.
No, but in terms of field theory, do you have any introduction into Lattice QCD? No. Most of you are just straight hard-nosed phenomenologists. Okay, so I'm going to therefore give my own short 5-minute introduction to Lattice QCD. And if you have questions, you can ask, because after that, we will switch to the calculations. So basic quantities which we want to calculate, if we were just think about it phenomenology, if I want to understand what is the impact of certain CP violating operators on neutron EDM, I presume most of you are familiar with effective field theory methods. So you take some theory at a TeV scale, you run it down to a GeV scale, which is that the hadronic world we live in. And so you have some set of effective operators, which are CP violating, and I will talk about that. But now, how do you calculate the impact of these operators, these interactions, on, say, the electric dipole moment? That is given by the matrix element of these operators within a neutron state, right? Now, most of you probably have forgotten how to ever calculate matrix elements. You probably, last time you ever did them were in undergraduate, right? You calculate Feynman diagrams, but how many of you have calculated a matrix element in the last 5 years? You have? Okay. So in order to calculate the matrix element of these CP violating operators, say within a neutron state, you would have to have a model for a neutron. The way we know how to calculate matrix elements is if you know the wave function of the state, then the matrix element is given by just so in quantum mechanics, you have psi bar operator psi, and let's say you have D3x. That's the typical thing which you calculate the matrix elements with. Where psi bar psi gives you the probability for, say, a particle at a point x, and then you can calculate for a given operator the matrix elements. So the quantity which we want to do, if we want to get matrix elements, is we need to know these wave functions. Right? The entire machinery of Lattice QCD is to give you this wave function. Because otherwise, people make models of neutrons, but those models are not very well controlled. They have systematic uncertainties because there's no small expansion parameter in which you can really expand your wave function. So the question is, how do you get the wave function, the fully non-relativistic wave function of a hadron? And the answer in 2 words is Lattice QCD. So that's, if you can understand a few of these concepts, I'll be a very happy person when I leave, because then I will have at least convinced 20 of you that Lattice QCD is useful. So now the question is, how does Lattice QCD give you the wave function of a state which is as complicated as a neutron? So there I will basically, can all of you see the board? So maybe can we put the screen up for a few minutes and I can.
We can go over there. This side of the board.
Oh, okay. So the first thing is, what Lattice QCD gives you is the vacuum of QCD. So, or at least 0 is Lattice QCD is field theory. So the best realization of understanding field theory is Lattice QCD. And basically everything you learn in field theory, when we have to do lattice calculations, we get hit on the head by that. All the things like renormalization, the whole subtlety of what operators are, and mixing between operators, everything you know about in field theory, we have to confront when we do lattice QCD. The second thing is, when you calculate matrix elements, you've never worried about the vacuum state, because the vacuum state in quantum mechanics is basically nothing. When you talk about a hydrogen atom, the vacuum in which you calculate that is basically nothing. There's no corrections from the vacuum and stuff. Whereas in QCD, the vacuum you will see in Lattice QCD is everything. The vacuum knows about everything which we want to calculate. And that's the part. So you need to get the vacuum of QCD. Then in this vacuum, you need to be able to put in probes so that you can somehow construct correlation functions. And I will describe each one of these points. So let's just call it probes. And the third thing is then to get the wave functions, which I'll just represent by psi. And once you have the wave function, then you can calculate matrix elements. All right, so how do we do this? The field theory which we do is we look at the path integral representation of the field theory. So I'll just call it d psi bar d psi du of e to the minus the action. So basically what you're doing is, how many of you studied the path integral approach in quantum mechanics when you do that. So the basic idea of path integral approach is if I want a particle to go from point A to point B, I look at all possible paths. Each path is weighted by e to the minus, in quantum mechanics, e to the minus I times the action. And then I allow all possible paths to go from A to B, each one weighted by their action. They interfere because this is the amplitude. And if I want to find the mean value of X, then I look at the value of X at a given time t and calculate just the average weighted by the weight, which is e to the I back. So expectation value of X is just sum over all the paths of X e to the IA. Okay? So that's the idea. So now let's start generalizing this. So instead of paths of a particle going from A to B, we have the universe. And that universe, we have made a small box and we have discretized it. That's the lattice. But in a field theory, we are always looking at the whole universe, so each of the paths is now given by your universe, which is discretized. And you, at each space-time point, you have all your degrees of freedom. Okay, so the analogy is, suppose you were doing a spin system, right? If you were doing an Ising model, then the configuration is the values of a spin at each point. And you have 2 to the n configurations. Because at every space-time point, you can have a spin which can be up or down. So the total number of configurations are 2 to the n. Those configurations are the analogs of paths. So now you go from there, from spin system to QCD, you have a 4-dimensional lattice. At each point, you have the fermion degrees of freedom and the gauge degrees, which are given by a SU3 matrix, which we usually just call U. So those are represented by 12 numbers or 6, or the independent ones are 9 degrees of freedom, which defined as SU3 matrix, or actually A. And at each space-time point, the 4 directions and over the whole volume. So the number of possible configurations, which in the spin system was already huge, now becomes infinite. Okay? So if we want to calculate any expectation value, we have to sample over these, just like you do in any other system. How many of you are familiar with spin models and stuff, or you never? So now you can see the complexity in terms of the number of configurations you would have to sample. So what allows some us practitioners any hope of doing a calculation? When you have at each space-time point, you have 8 degrees of freedom, just the gauge degrees of freedom. And these are continuous values because each point you have an infinity because they're continuous valued, and then you have an infinite number of points. Even if you have discretized them until we shrink the volume down to a point. So the reason you can do this is because this function, which now for field theory becomes in Euclidean time, e to the minus s, this quantity is extremely highly peaked. So there is only a number of configurations you have to sample is in this region where this one is large. So now the next step here is, again, how many of you have done numerical integration?
So before going there, just out of curiosity, do we also have some gauge degree of freedom on the lattice?
Yes. So the quark degrees, thank you, I was going to come. Fortunately, the action of quarks is bilinear. And we can do Grassmann integration over the quark degrees of freedom. So this basically is equal to just the du determinant of the Dirac matrix e to the minus s gauge. Okay, so this is gauge plus fermions. You can integrate out the fermions.
Yeah. And is it the same for also ghosts? Like, we know that in QCD, like we have to introduce, like, if we compute the loops, then we have to introduce the ghost, right? Like a BRST and
Sorry?
the gauge degree of freedom.
The gauge degrees of freedom on the lattice, you don't have to worry about, because all you worry about the theory is gauge invariant. Because what happens is, yes, if you don't fix the gauge or you don't worry about it, you're counting many configurations which are gauge equivalent. But as long as you're doing your sampling in a way where you're not on gauge equivalent orbits, you don't really even need to worry about.
Okay.
But yes, technically, yes, all those things you have to think through. But it turns out that you just don't need to worry about that, making sure that you're not just getting your sampling in terms of just gauge equivalent configuration. But the way we do the sampling pretty much guarantees that you don't really are sitting on a gauge orbit and you're just sampling the same gauge equivalent configuration.
Okay.
Okay, so now coming to back to the integral. When you do an integral, let's say you were just doing a very simple integral. What you do is you generate points. And then you just calculate f of x. And your integral is just sum over f at each of those points times dx. So you just take these little volume areas and you just sum them up, right? So, but now suppose you had, and you could do this by uniform distribution of points along this x-axis. But suppose your function was extremely highly peaked. So it was almost like a delta function, which this quantity is. Then if you just took a uniform distribution of points, you would get a lousy approximation for the integral. So all of you who've done numerical integration, you know there is something called importance sampling, where if you generate your points over which you sample your function, depending on how large the action is or how large the function is. So importance sampling plays an extremely large role. So basically, what I've told you is how you go from this double infinity continuous valued functions at each space-time point, how you can basically get away with doing your integration, keeping maybe 1,000, 10,000 sampling points. Because of this importance sampling, that you're actually sampling where the integral is large. And it turns out that, I mean, it didn't have to be, but it turns out 1,000 to 10,000 such samples are sufficient. Now, this is these configurations. So what is these 10,000, let's say, I'm going to just use the number 10,000 configurations. What are they? They are snapshots of your QCD vacuum. So you have these fluctuating gauge fields. And those gauge fields are in a stochastic way defining your vacuum. So you have constructed the fully non-perturbative vacuum of QCD, but you have no clue what it looks like. See, think about it. When you do perturbation theory, you never think about the vacuum. You put in your electrons or your quarks and stuff, and your background you don't care about because you're just building up, oh, I have another interaction, I'll add another loop or I'll add another thing. But the vacuum you don't think about as this non-perturbative, highly sort of sophisticated quantity. But here, each of these configurations which you did are snapshots of your vacuum. Okay? And this vacuum, you will see, knows about everything you ever want to calculate. It's the vacuum which knows about it. And I'll show you how we do that. Okay, so is this clear so far that we generate the vacuum of QCD through sampling, generating configurations which have this Boltzmann factor e to the minus s. So once we have the vacuum, which is these configurations, then on this we can calculate. So you have the Dirac action or this thing which is defining the vacuum, but then you have the interaction. So suppose I put in a quark here and ask what is the propagation of this quark from one point to the other. The interactions of this are given by my Dirac operator. And you know that the Dirac operator is the inverse, or the inverse of the Dirac operator is your Feynman propagation. Where this Dirac operator is a functional of these gauge fields which you've generated. So this is the background gauge thing. These are your background gauge fields. And on each one of these background gauge fields, you have a Dirac operator. And you calculate the inverse because now it's a matrix, it's on a finite width. And that is your Feynman propagator, which gives you the amplitude for a quark to go from a given point with a given spin and color index to another point. Okay? So that's all you calculate. So when we do lattice QCD and we want to calculate matrix elements, the basic quantity we calculate is the quark propagator going from point A to point B. So now you should ask me, how do you get physics out of it? All you're telling me is you only calculate the quark propagator. So what do we do? Suppose now we want to get the properties of, let me go back here. I hope you can see it. Let's say I want to calculate the matrix element of some operator between a neutron state. All I know is the quark propagator moving in that background gauge field. And I know my neutron consists of 3 valence quarks. And so here is I create a neutron and I annihilate a neutron. So I create it and I annihilate it. And it propagates for some time. How do I construct this? So basically what you do is you take this quark propagator I calculated, and you start and you basically stitch together 3 quark propagators with the appropriate spin and color indices so that, so here is your an operator for creating the neutron, which is written in terms of 3 fields of quark fields, Q1 with a charge conjugation, there's a thing, I'm trying to. So some operator which defines a neutron. But this looks like a free thing, 3 things, but with this thing and the quark propagators, each one of which has spin and color indices. So it's I, J, A, B, X, Y. I basically stitch together so that I can now construct, instead of a quark, it is a neutron. Because defined by the end things of the operator. So I just take, it's just stitching together 3 quark propagators with the appropriate spin and color indices. But now the question which I used to, initially, I just told you I calculated a quark propagator. You're telling me by just stitching together 3 of these propagators, I have the full neutron state. How could that be? How does the quark propagator know anything about the neutron? All you've told me, you combine the spin and color indices appropriately, and I've given you a neutron. How does, if I had combined a quark and an anti-quark, I would have gotten a pion or a rho meson. Or if I have different spin and color combinations, I could have gotten a delta. How does the quark propagator have any idea of what it's going into to give you a neutron or a pion or a rho or a delta. Anybody can answer this question? This is a test. And this is where the beauty of the vacuum comes in. So remember, we are doing the integral by approximated numerically. In each of these configurations, we have calculated this quantity. On a given configuration, knows nothing about the neutron or nothing about the pion. You've just constructed a correlation function. Okay? But when you do that path integral, which is that numerical approximation you're doing, each of these configurations is fluctuating. Right? That's what, I mean, the values of these U's are fluctuating or different. This thing which you have put into it by externally putting the quarks there is picking out those fluctuations which correspond to a neutron propagator. So the vacuum already has these fluctuations. And by doing this sampling, on each configuration, you calculate this correlation function, which knows nothing about a neutron. But when you do the path integral, that's where the fluctuations which correspond to a neutron get reinforced and everything cancels out in that correlation function. Okay?
But how do you know what exactly to sample to get a neutron?
What? Sorry?
So in a sense, you're saying that your distribution function has actually several peaks, one of which corresponds to a neutron.
No, not one. The peak doesn't. The peak is the Boltzmann factor.
Yes.
You are taking a representative sample of the vacuum. The 10 to the 4 configurations are giving you snapshots of a vacuum.
Yeah. In the vicinity of the peak. Right? So
The snapshots are where this peak is large.
exactly.
Okay.
Exactly. But so there will be another peak which corresponds to not a neutron, but no.
No, there is no other. So first of all, the nice thing is this function is single peaked and huge in one thing.
Yes.
It's not the peaks which are telling you a neutron or a proton or a delta or a pion. It is the fluctuations of these things. So think about the vacuum as this highly fluctuating thing, right? You know that you can pop a neutron out of the vacuum and it can go down. It just suppressed by the energy factor. So think of this bubbling vacuum. You have a neutron which is popping up somewhere. So imagine now a vacuum fluctuation in which a neutron pops out of here and gets annihilated here. Okay? So, or it could be a pion flux. It's the same vacuum, it's the same fields, right? In some configurations, you will have the neutron popping up here and annihilating. In some, you could have at the same side a pion or star. When you put this external probe, it is picking up those fluctuations which have the quantum numbers which you have enforced by hand.
Automatically.
Yes.
But okay, so they don't peak like some excited states of neutron, right?
Hold on. I just said the quantum numbers of a neutron.
Yeah.
I did not say anything about ground state or excited state. I'm saying it picks up a neutron. Okay?
Okay, well, okay.
Including N prime.
Yes. It all it cares about is quantum numbers. You have no way, we haven't enforced anything else about a neutron. Because remember, the fluctuation, what you mean by a neutron is the full Fock state wave function of the neutron. Because you have no way of saying it's only 3 quarks and not 3 quarks plus 1 quark and anti-quark which is a neutron plus a pion and stuff like that. Because the vacuum creates all those things. So you've never seen field theory. Maxim, you will have to show them that this is really what field theory is doing. This is really what field theory is doing. If you understand field theory, that's exactly what it's doing. You have the vacuum fluctuations know about every particle in the universe. It's just that the fluctuations, as you get higher and heavier, they are smaller. So you would have to do far more samples if you wanted to simulate you. But the vacuum knows about everything.
So I heard that, like, in order to separate between the ground state and the excited state, they both have the same quantum number. Like, you can also control the distance between them.
We'll come back. So hold your horses there. We'll come back to that next step in a minute. So right now, just think of how exactly am I going to calculate matrix element. I've shown you now how out of the vacuum you're picking up a neutron propagating from point A to point B. All right? Yes.
So you had said earlier that like a lot of this is much simpler in like a perturbative theory like QED, like I don't have to think about the vacuum stuff.
Yeah.
But a lot of what you've just said seems like it can also apply in that case. Like in QED, I can like the vacuum can include like creating an electron and then annihilating it.
Yes.
Right.
And but you do those in loops. So when you talk about a vacuum creating that, in perturbation theory, how do you implement that? You add a loop.
Mm-hmm. Yeah.
Through an electron emitting a photon going into a quark loop and stuff. So, and that popping out of the vacuum, you're doing by adding by hand a loop after loop after loop. But here, what the non-perturbative part is, you have to take into account at the same time the infinity of these at all orders, because there's no suppression because of a coupling constant.
Okay.
And these fluctuations, because the quark propagator knows about the full vacuum of the theory, it knows about all those fluctuations. So all those fluctuations are already there when you build this in. That's the vacuum fluctuations. Okay, so now we've said that how it's this beauty of picking out those fluctuations out of the vacuum which correspond to a neutron.
Sorry.
And yes.
I have a question here, but you said you will have to go to Euclidean space so that you have this peak.
Not, you don't have to go to Euclidean.
Because then how do you have to go back, right, to Lorentz?
So I'll come back to extremely good question. So the reason we work in Euclidean space are two. So first and foremost, by going into Euclidean space, you take a quantum field theory and convert it into a statistical mechanics system, without which you cannot do anything. So now you have the standard Boltzmann way, and you can do that. The second is that these big contractions, which you want to write down for any correlation function, now can be sort of decomposed into these quark line diagrams. And I'll explain what that means in a minute. And yes, eventually to get physics, you have to go back to Minkowski space. And I'll tell you why we get away without having to do that, because that's an ill-posed problem if you actually had to do the rotation back.
Right, okay.
Okay?
Yeah.
Sorry, I'm going to get nowhere near my seminar, but I hope you already know my seminar, so you're not worried. But should I continue in actually explain to you how Lattice, or what the things are about connecting field theory to Lattice QCD, and how in a very my own idiosyncratic way. So, okay, so you've now done this. So how do you now calculate matrix elements? So this thing, if you wrote down, would be written as a time-ordered product of a correlation function of an n bar at point X, point Y, between the vacuum states. right? That's how you would calculate it. And if you were to do this in quantum mechanics, you would have to make a model of what you mean by the neutron. Here, I'm telling you that we get it exact, the fully quantum mechanical one. To get any matrix element, you calculate the same thing, take the time order product of, and then you do an operator at some point Z in between. You agree this is what you would have to calculate if you were calculating a matrix element? But now the question comes up is, how does this give me what I had originally written down, which is psi bar O psi at a given time, D3x. And that's the next part I'll explain to you, how from this correlation function, you can get the matrix element. So let's just take this. I'm going to now draw this in a sort of, let me just leave it here. I wrote down this operator, which has got the quantum numbers of a neutron. But as all of you said, this is a local operator. It is going to create all possible excitations of the neutron, which have the same quantum numbers. So even if I had created a pure neutron by a miracle, if I had done a very good job of my operator, the moment it propagates, you would have a gluon coming up, creating a quark anti-quark here, and then annihilating, right? This is something which you know can happen in quantum mechanics, right? Now you draw a line, so this is, let's say this going this way, and here are your three quarks. You cut your diagram here. What do you have? You have a neutron plus a pi. And all those fluctuations, remember the vacuum is taking care of all those fluctuations. So in this correlation function, you have the full Fock state wave function. Because you are in Euclidean time, this amplitude for a neutron to go to from point at time 0 to time t decays like the mass of the nucleon times this time t. Because in quantum mechanics, it oscillates e to the I omega t. In Euclidean time, it gets damped. So the beauty of now going to Euclidean time is all the states which are propagating, you have no way of isolating them, but as they propagate, they are getting damped by this exponential factor. So if you wait long enough, you can isolate the ground state.
So, if you want information about higher dimensional state, you would have to subtract the ground states. Is there known ways of?
So there is. What you do is you write down a variational wave function, and then you calculate it, and you can get all the transition to matrix elements and stuff, which is a decadal problem. It takes, I mean, the cost goes up. So is everybody clear on what I just did? Okay, so the states are dying off exponentially. So now take the same thing. Now I want to do this. So I'm just going to make this a simpler thing. Here's my neutron. And now I'm putting in this thing in the middle. Okay. Now think about this, that this is creating all possible states. But if I wait long enough, every state is getting exponentially damped. And in a finite box, your spectrum is discrete. So you have mass gaps, which means if I wait long enough, all the excited states I can kill off. And at this point, only my ground state is left. In general, if I start off, here you have a sum over all possible states, but they're all evolving. And by this time, only my ground state is surviving up to some precision, which I want to measure. So the T has to be large enough that that precision is satisfied. Similarly, you can reverse it. This thing has to be large enough that only ground state is there. Right? So this, now, again, go back to the wave function. I have 10,000 of these snapshots, right? Each of those snapshots, I look at what is happening to my correlation function here, just before, at the same time, where I put in this operator from both sides. This snapshot of my correlation function is giving me the ground state of the neutron. And again, it's these fluctuations. You have you cannot visualize it. It is again a numerical stochastic thing of what my computer is giving, has those numbers for this correlation function. But that distribution corresponds to the ground state of the neutron.
Actually, I have a question about something you said earlier. So you said because you're putting it in a box, then you've discretized the spectrum.
Yes.
Right. So I would think that's fine as long as you like don't have like good enough energy resolution to see like that your spectrum is discretized. Like as long as you're sort of looking at it on coarse scales, it's fine.
So if you were in an infinite box, the first challenge you would see, I told you you can have a neutron. Let's say I created this at zero momentum because I can project onto a momentum here on X. I can just, these are at X, but I can always do sum over X. That's a operator projected onto zero momentum, right? But now zero momentum means I can still have this state. This has perfect quantum numbers of the neutron. Okay? So all possible values of P are now allowed. If I took the volume to infinity, this P, there is no gap between the P. The momenta are no longer discrete. So you now have a continuous spectrum.
Yeah.
So I cannot now use this trick because I have infinitely small energy resolution. So there is no damping. I can't damp out because a state which has a tiny amount of momentum, I cannot get rid of using that exponential damping.
Yeah, but I guess that's sort of my point is it seems like you're taking advantage of a mass gap, which is just there numerically. Like it's not like there's no physical.
Yes,
mass
but
gap
eventually
totally.
what I want to do is I will take all these limits to infinity.
Yeah, but there's like an order of limits issue here where you're like taking the time to infinity first rather than
So
box.
yes. So
is that okay?
What I'm doing is I'm isolating the state by putting in this mass gap, right? And then I can take my limits.
Yeah, I guess I'm. It's not clear to me that that's an okay thing to do.
Why? What is it? So I'm calculating the matrix element within the ground state. And I've gotten rid of all the contributions from higher states. And now, as I take to infinity, my ground state becomes more and more realistic. I don't have, the excited states have always gotten rid of, they have no contribution. So they never contribute as I'm taking the limit. Within the accuracy, like 1%, 0.1, whatever, because it's numerical, that's where it kills you, that you always have. Every statement I make is a certain degree of accuracy. Okay? So what you do is you isolate. So what is happening is on each, at that time slice, coming from both sides is now the stochastic wave function of the neutron. And now you can put in any operator you want, whether it's axial current or a CP violating operator, you get the matrix element between the neutron states. Because remember, in quantum mechanics, this part never changes, this part changes and gives you different physics. The same thing, you've isolated the neutron and you do it. Now comes the next important question is, but this is all in Euclidean. Okay, And here are the two beautiful things. This energy, when you rotate, the spectrum as you rotate from Minkowski does not change. It's your same, the spectrum does not change. The spectrum of the theory, all that happens is it's now the transform matrix which is taking you from time to time. But the spectrum of that transform matrix is the same as the spectrum of QCD. So if you now fit this function, you will get the spectrum of QCD. The second thing is matrix elements, which I've told you, are calculated at a given time. And those are the same in Euclidean and Minkowski because again, you're calculating them at a fixed time, but not at separate times. Anything that you have to do with separate times is a mess. And those are response functions and stuff, which is a nightmare. But equal time or a fixed time, you again, when you rotate it back, it's just the same thing. There's no thing. So these are some of the beauties of how we get away with it, even though we rotate to Euclidean, and then we don't have to rotate back to Minkowski, because these quantities, equal time quantities or given time quantities are the same in Euclidean and Minkowski. Okay? All right. So you have the wave. So these are the two most beautiful things Lattice QCD gives you. It gives you the vacuum. And now you, for the first time, I hope you've appreciated that the vacuum knows about everything. And that's why we have to get the topology right, because that's a property of the vacuum collectively. Instantons and all things will actually contribute to certain correlation functions. So the vacuum has to be right. And once you get that, that's a stochastic concept, and the wave function is a stochastic concept. And that's why all you guys hate Lattice QCD, because you don't have any intuition of what the hell is going on. Because it's all in a computer, it's all numerical. As this distribution of your gauge fields, but you have no idea what it means. But it's better than making a model which you can't control.
And the spectrum here, the hadron spectrum is actually done quite well now via this technique.
Yeah. So we have
like 1%, right? Is it?
Yeah. So we have phenomenal convincing evidence in many cases that it, after all, it's field theory. I mean, if it's wrong, then QCD is wrong, or field theory is wrong. So, okay. So I've taken a large amount of time just explaining what Lattice QCD is. Because if I can leave you with saying what Lattice QCD gives me, anytime I need a matrix element, I need a hadronic state, I have no choice but to go to Lattice QCD, because I have no way of modeling the hadron, which is controlled.
I think you've made.
Sometimes you can extract it from data with extra assumptions.
Yes. But if you wanted first principle, then it's yes.
I think you've made the case that we should at least give one lecture on this if you're giving a QFT course.
Yes.
Give a lecture like this would
Yes.
be nice, or 2 lectures.
Yes.
It's worth it. Yeah. It's very
Yeah.
nice. Yeah.
Because this is when you really
We don't do this in QFT when
Yes.
we give QFT.
Yes, because you don't, that's why I said, if you do Lattice QCD, you really have to understand what is it in quantum fields, what are the essence of this whole thing.
Yeah.
So I hope I can leave you that. So now let's get back to, so I hope some of these things will become simpler and stuff. And thing is that, as I said, this thing is only asymptotic, but if you don't have the separation large enough, then you're screwed. Because then excited states are contributing, you're not getting the matrix element in your ground state, you're getting it in this fog state wave function, which is not what you want. Well, actually, you want but you don't want the contributions from excited states. And the part where you don't want it is, so you create a neutron. What you don't want is that loop effects like a pion are fine. But when this pion comes on shell, then you don't have a neutron state, you have a neutron and pion state on shell. And that's not what you want as your Fock state wave function. Virtual things are fine, but not on shell. So you have to isolate that contribution. And that's one of the big problems in nucleon matrix elements. And a simple way to explain that is if I'm looking at a pion, sorry, another digression, I'm looking at this two-coupon correlation function. The variance of this is given by 4 lines, right? You take the correlation function, you square it. That's how you calculate variance. So the correlation function was this, you square it with a joint. This is 2 quarks and 2 anti-quarks. The lowest state you can write down of 2 quarks and 2 anti-quarks is 2 pions. So the signal here is going as e to the minus m pi t. This quantity, the variance is going as e to the 2 m pi t, which means the error is also going as e to the minus m pi t, or the thing. So the signal is falling off this way, but the error is also falling off that. So the ratio of the signal to noise is a constant. The challenge with neutrons is 3 quarks, 3 anti-quarks. What's the lowest state you can create out of that? 3 pi. So therefore, the signal is going down e to the minus m pi t. The error is going down as e to the minus 3 m, sorry, and neutron t, 3 m pi t over 2. So you have to take the square root. This number is 200 MeV, this is 980 MeV. So the noise is growing very rapidly. So in the case of a pion, I can go to infinite separation, my signal doesn't degrade, here it's degrading exponentially. So that the challenges you were worrying about, how do you isolate a ground state, are just phenomenal in nucleon correlation functions, which is one of the big things we are fighting against. Okay?
But actually, going back to the picture you drew there, so can I, like, if I wait a very long time, like before I've done the operator insertion, I wait a long time, so I get rid of all the pions and I just have the neutron ground state. Or like I've isolated the ground state.
How do you get rid of them? They're floating all over in the vacuum.
Okay, I mean, I guess maybe that was kind of the question I was going to ask. Isn't there always a probability for the pion to pop up like right before I have the operator and then go right after? And
as long as it's off shell, that's fine. As long as it's virtual.
But isn't there a probability for that to happen on shell? And then it'll be suppressed by e to the minus m pi t, but the t there is just the t over which it's alive.
The total separation you have to make. It turns out it's the total separation which you have to worry about.
Oh, regardless of like how long the pion actually exists,
right.
It's the total t that
Yeah.
matters. Oh, okay.
So because if you take it infinite, then basically you have gotten rid of the excited states. Or the excited states which are created initially by your operator. The things which are popping in between, they are part of your Fock state wave function, which you want to include. Because that's your real neutron.
Oh, okay.
So it's only those parts which are, because we have no way of isolating just a neutron unless we do a very complicated variational thing. Those things you get rid of, which are, and anything which goes on shell. Okay, all right, I'm almost out of time. 10:15, so I can Now, very quickly, I can cry over, we have lost half our collaborators. That's a disaster. Because these calculations are hard, and if you don't have working hands, you are in trouble. So our Vincenzo, who was really an essential part of this whole thing in terms of effective field theory and the things moved to INT, and Goram, who was our computational guru, has gone to NVIDIA, makes enough money to, so, all right. So here, I mean, just listed the 6 papers on which we actually published almost all our work. So now let me just go on to, I'm going to skip, I presume all of you know why we are calculating the electric dipole moment of the neutron. Does everybody know that? So, okay, I don't have to tell you this. Here, just to emphasize that the next decade is going to be very exciting because we are so slowly ruling out everything. There seems to be some miracle God sitting there and saying, we are going to keep all these details hidden from these people working away. So if the next generation of EDM experiments, Neutron EDM, which is the one at Oak Ridge, the SMS EDM, doesn't see that, then a large part of our BSM theories are going to be ruled out. So it's already the electron EDM is ruling out a huge amount of baryogenesis models, or has ruled them out. And if you don't see an EDM in the next 2 orders of magnitude, then most BSM physics or models are also ruled out because BSM models automatically generate more CP violation, they have more phases, and then basically they all predict values which are already being slowly and steadily ruled out.
But doesn't it mean that you just push the scale up of the new physics? That's
Oh,
all.
but then, yes, but then that is always a cop out. But anything which people talk about gets slowly and steadily, yes, you have to keep pushing them to higher and higher scale. Right? Because there's no way, that's always a way out.
Okay.
Okay, so this is wonderful work. Maxim did and taught us that there's a whole bunch of operators if you have fundamental CP violation at whatever scales. And if you look at them, at low energies, they introduce a certain set of operators you can organize by dimension. The most important of those are the theta term, which is there in QCD by itself. Then there's the quark EDM, which means the quarks itself can have an EDM, and that then feeds into the neutron EDM, or the interaction of the quark with the gluon fields can have an EDM, or gluons can have, through their interaction, have an EDM or contribute, which is the Weinberg, the 3 gluon term, and they all contribute to the neutron EDM. Because, and you can write that contribution in terms of, at low energies, operators composed of quark and gluon fields. So your basic CP violating Lagrangian is your standard CKM Lagrangian plus the theta term plus all these operators which are coming from some BSM theory. This thing is there because it's a dimension 4 operator, so it can be there in QCD. You don't need to invoke BSM physics, but all the other operators are coming as effective low dimensional or operators from some heavy particles which are there, whose interactions have CP violating phases. And at this point, we've already pushed that scale up to TeV or more. Okay, any questions on that? So these low energy operators, except for the theta term, you can see they're all in terms of quarks and gluon fields. There is one which is the quark EDM, which is the interaction of the quark itself with the electromagnetic current, which is the F. that vortex itself has a CP violating part, and it makes it a special case. Then there's the quark chromo, which is coming with this interaction with the gluon fields, the Weinberg, which is the 3 gluon, and then you have 4 Fermi in operators and higher operators. But in the organization of how large we expect them to be, these are the dominant operators which we want to consider, whose matrix elements we want to calculate. So hopefully now you all are experts, you can all know how to calculate matrix elements, which is calculate your vacuum, calculate your quark propagators, and then stitch them together to create these what are called quark line diagrams. Okay, and then pray that you've taken them far enough apart and stuff, and I'll give you examples of. All right, so we start, let's just start with, I mean, I've already talked, I'm not going to. So let's start with the thing which we can calculate. There's only one operator for which we have results so far. After 10 years of work.
So tensor charge.
Yes. And that's because of that special case I mentioned is of the quark EDM, because this quantity you add to the Lagrangian. Now, how do you define what an electric current is in quantum field theory? You calculate the Noether's current with respect to the thing. So the moment you add that, that contributes to the electromagnetic current. There is a CP, which is exactly the coupling of the quark to the vector current. And that is, when you do the derivative with respect to AU, what you end up as getting added to your electromagnetic current is just the tensor operator Q bar sigma mu nu Q. Okay? And that is the tensor of bilinear. And we know how to calculate that. But what does it do? So you have to calculate this matrix element. This gives you a charge plus the standard spinor, the sigma mu nu, that's what it's proportional to. This charge is the quantity which tells you how strong is the contribution of this operator to the neutron EDM. And in addition to the matrix element, you have the coupling. And this coupling is what effective field theory gives you. It says you start off in some BSM theory, it has CP violating couplings. You do the renormalization group to 1 or 2 GeV. Then the couplings of your effective operators are these Ds. So the contribution is the coupling times the matrix element. Is that clear?
We have actually done a perturbative calculation for heavy quark that you can integrate out in a certain limit, gives
Yes.
the light quark a. It would be nice to compare what you have for this DC. We compared to our perturbative calculation.
Yes, the problem with DCR is at this point, it is a tiny number.
Yes, indeed.
And
Which is not a problem for analytical calculation.
It is a tiny number, and our current calculations have an uncertainty of 100%.
Okay. So better use our answer.
Does your number fall into their range?
So how small is it? I think it's 0.0. See, in heavy quark, basically, this coupling.
If you integrate out, you get a very specific 3 gluon operator, the tensor operator with DABC structure. So you could forget that and just do that average, and not so it would be like a similar to Weinberg operator, but instead of FABC, it will be DABC, and the 2 indices will be sticking out. So if you can take that matrix element, you would automatically do B quark or T quark or anything.
Right. So the only reason that can be is that your BSM theory, the CP violation is coming through some sort of Yukawa coupling. So so the couplings, these Ds are proportional to the quark mass because that's what the Yukawa coupling is. So in those models, contribution of B and T quark can be large, and that's where you can do analytical stuff. But we are more concerned with these lighter ones and see what their contribution is. Okay, so this is again, I'm showing you the quark loop diagrams. Now, remember when you're doing CP violation, you have flavor diagonal operators. It's U bar, sigma mu nu, U, or D bar, sigma mu. Each one of them is contributing. So when you put an operator, you can have two things, a U going to a U, but the operator can also be attached to a vacuum quark loop. So your neutron is going along, it pops a gluon, which goes into a quark loop, and your operator sort of attaches to that. So these are called disconnected diagrams because the quark loop is disconnected from the neutron quark line. The gluons I'm just showing to show that there is a connection, because all possible gluon exchanges are allowed. So in literature, when you look at lattice calculation, these things where the operator attaches to one of the three valence quarks is called connected, and these are called disconnected.
And just like I said, you would need three gluons for this.
Yes.
For the test.
Right. So here is the numbers which Maxime was talking about. So what you can see is that if you have theories which have these couplings, these CP violating couplings from Higgs-like thing, then you want to calculate the heavy quarks because the couplings are growing like the mass of the core. The matrix elements are falling like 1 over the mass of the core. And the total contribution, the product, could be large. But at this point, you can already see the strange quark itself is hard for us to get a number beyond few sigma. So the charm, the people.
This operator is actually charge reversal odd sigma mu under the charge symmetry. And so you can rationalize it by saying that the number of S quark and anti-S quark in this case will cancel out compared to say gamma mu gamma 5 operator,
Right.
which is charge even and where it doesn't cancel.
Right.
Or you can, in perturbative language, you need three groups to communicate the S quark to the rest. Three groups. You think of the S quark as a loop, then you need minimum three groups.
Right. So, but I mean, this is where we are.
Okay.
So now, how does this actually help us in the physics? So we have values for these charges, right? Remember the contribution to the neutron EDM is given by the sum, and you could have bottom and top quark also there. In principle, we today know only one number, which is a bound on the electric dipole moment of the neutron. Okay? So how do we use this in phenomenology? So let's assume that there was a model in which the CP violation was entirely quark EDMs. All the other operators did not contribute, but there was no operators generated. Then I can use this equation, knowing these values, to invert for them and see what ranges of couplings are involved. It's a very ill-posed problem because you'll have a large space, but it does give you some constraints. So that's exactly what we've done here. So this is a priori. If I just look at up, down, and strange, then given the current bound on the EDM, we can get a bound or this volume in this 3-parameter space of the possible allowed values for the D, U, D, D, B, S, correct? So that's the constraints which we afford. Here, this is a particular model, which is the split SUSY model, which just so happens that in it, the dominant operator is the quark EDM operator. And then we can say, okay, if we have these constraints on these three couplings, can we put some constraints? So it puts certain constraints on the ratio of the neutron to electron dipole moment. And that's how it impacts phenomenology. So this is just an example of how knowing an experimental value or bound on the EDM, knowing these matrix elements, you go back. But the problem is extremely sort of, you can see there's a single quantity which is then giving you the constraints, but even these constraints are actually very valuable for figuring out which DSM models will survive.
Sorry, why do you have two twos in your contours then?
Sorry?
Is that right? Am I reading it correctly? You have dn over de is 2, but you have it twice. Should it be 1 maybe?
Wait, I'm trying to remember. I think it comes back. It's a ellipse kind of thing.
Ah,
So it comes back.
Oh, it comes around.
Yeah.
I see.
Okay. So this is, in a nutshell, what I've given you is how you do the lattice calculation, how you can calculate a given operator. In this case, it was very simple. It was the tensor charge. I've hidden all the other details in the error. The next thing is the sigma term. And I will end, if I can have a few minutes, I'll end with that, because that shows you some of the problems where even this one we cannot calculate.
Can I ask you a simpler question? So the neutron EDM is a complicated observable, but if I am to calculate neutron pion vertex with vanishing mass of the pion, so vanishing momentum, right? Then I can use a low energy reduction, I don't do lattice, right? I would just approach this. I would know that this whole thing will be proportional to U bar U minus D bar D matrix element over the nucleon, which I can read off from a similar paper on the scalar charges, right? And that is a 3-point function rather than the 4-point function where the neutron EDM is more complicated, right? So has anyone tried to do the pion nucleon coupling constant induced by theta trap? Because we have a prediction for that, right?
Yes,
from Veneziano with De Vecchia papers, right?
So what that requires, we have to work in this effective field theory approach of looking at a pion nucleon coupling and then looking at the CP. So there we have to calculate up, and we should be doing it instead of the electromagnetic current. You have to do exactly what you said, the axiom, because that's what gives you this gamma mu gamma phi, and extract exactly the CP violating.
Well, in some sense, we know the answer. So you'd be testing whether your, the low energy theorems that you believe to be true are satisfied on the lattice, right? So that is.
Maxim, we got to do a lot of stuff. We're just suffering from lack of hands. So in the case, just to give you what these spot level diagrams are. So basically, when you're looking at the theta term, you're looking at the interaction to probe EDM, you're looking at the interaction of the electromagnetic current with the neutron propagating. This is what I just showed you. But now you are also looking that this has to be done in the presence of your topological charge. So that in this case, the topological charge of the operator is the volume integral of GG twin.
Except that you cannot write a two gluon vertex perturb it.
Oh, yeah, again, yes, I'm stupid with my drawing of, these should all be three gluon, this should be a.
Well, no matter how perturbative, there is no perturbative description of a theta term.
This should be three, I have to change this to showing three gluons.
So,
And the same thing here, there should be another gluon, because it doesn't couple to two gluons. But basically, yes, as long as think of these as three gluons, and then these are the two kinds of diagrams. So there's the disconnected, because the electromagnetic current is diagonal in flavor, and there is the connected one. And because it's a volume integral, this insertion of this GG twiddle, what it does is essentially weights your calculation of the insertion of the vector current by the topological charge. So this is essentially doing a reweighting of that thing. And so now you see, in order to get this right, you have to get the topological sectors correct. The fluctuations in those configurations which are giving the fluctuations of topology correct. So here is what we did. I mean, and this is now going to go into more technical detail, which I have not introduced in terms of, is that when you calculate topology on the lattice, it's not as simple, which you would have thought, oh, this is just GG twiddle. I know how to construct G from my link variables. Why can't I do it? The challenge is that when you construct that, you have fluctuations which have to do with small instantons, which are just lattice artifacts, popping in and out of the vacuum, and you have to get rid of those. And the way we do it today is we make our configuration smooth without changing the long distance physics, which we are interested in.
sorry, is this a susceptibility with light quarks or without?
Yeah, all the configurations are with light.
With light.
Yeah,
Can you prove that it is proportional to mu times md over mu plus?
yeah, we basically get results which are consistent with the chiral perturbation theory value for the susceptibility. So we are getting the topology right. There is, I mean, right meaning, as I said, there is still an issue of how do you define topology on the lattice, but different definition, we can get the right thing. And so what we do is we smooth out the configurations without changing the long distance physics, which is the physics we are interested in, to get rid of these small, what are called dislocation. These are instantons of size, essentially the lattice spacing. And these figures show that very quickly, if you do a little bit of smoothing, the distribution basically becomes stable. But it takes a long time of smoothing for it to become an integer charge, which is what, if you could do topology correctly on the lattice, a lattice should have, the topology should have integer charges, which it doesn't, but if you smooth it enough, it does tend to that. But the nice thing is that to calculate the susceptibility, what we need is the distribution and not the fact that you actually get integer charges on the lattice. So we can get the susceptibility, so that's the first kind of thing that we are doing this correct. I'm going to skip all this, and I'll just point out that we have a challenge. And that challenge is, which I'm going to leave you with, because if somebody can solve this, this will be phenomenal. So this is the data where each of the colors is telling you how far apart the two nucleons are. And the individual points are telling you where in between I'm putting the vector current. So if I could take the neutrons far enough apart so that only the ground state is there, then I would have a region in the middle where I would get no contributions from excited states, and I should get a flat section. I don't. So what we have to do is we have to include the excited states to see how it approaches that. And the fit here is shown, the colors are the fit, assuming the spectral decomposition of how this three-fold function should behave. And this black line is the value you would get by extrapolating this separation to infinity. But the problem we are running into is that this data is the same as this data. Here we have assumed that the n-pi state, which I've shown you can arise, right? It's part of, it has the same quantum numbers of a neutron. It's momentum 1 unit and -1 unit. If you put that in, you get this as your extrapolation. Because the mass gap of an n-pi state is much smaller than your radial excitation. Because that's at 1440, an n-pi state is at 1200. And when you do this extrapolation using the spectral decomposition, you get this huge difference in what your value is. So this is where we are stuck. So I'll just sort of finish here. So these were our results. And if sometimes you will see this, that there are 5 collaborations who are claiming to have calculated it. Our errors are very large because we are the only ones who are worrying about whether an n-pi state contributes or not. The second problem is that at least in 2 of the calculations were done at very heavy quark masses. So like, for example, these are the 3 values of pi mass or quark mass, where the calculation was done in a collaboration called Theta QCD. And they've done a fit assuming chiral perturbation theory, but also demanded, which we know is correct in chiral perturbation theory, this contribution should vanish at 0 quark mass. And that forces that you have an exact point at 0. So therefore, these 3 data points, you have to curve out. You have to get a value where the errors become artificially small. So look, I'm not going to. So the same thing happens here. This is another collaboration, which is Andrea Schindler. Again, the pines were around 400 MeV or higher. The curve is done, but again, demanding that it goes to 0. So you get it curving. And so that's where we are. So we have a problem of understanding the excited states and how much they contribute, because you can see that this contribution is huge. Yes. So here it's a 0.001. Here it can be minus 0.025. So it's not a trivial thing, but if I did this extrapolation, you won't believe it. If I went from here to here, saying, how do you know because we only kept one intermediate state, how do you know there aren't other states which are contributing? So at this point, at least as far as we believe, or we don't believe we have a number which we can definitely even give for the theta term. So let me stop there.
Okay. Thank you so much.
What are the questions that you have that one has?
But usually we have, Russian professors keeping the speakers
In control.
from moving from slide 1, but you did your job yourself. That's appreciated for the lecture. So, are there additional questions?
So you think I should do a couple of talks on quantum introductory first? No, it should be in the middle because you have to know a little bit of field theory.
Middle, yeah.
Yes.
If you write up your lectures, right, in a concise way, that would actually be very nice. Right.
So question, how many of you had thought you understood field theory and the role of the vacuum.
Okay. I have a different question. So there is a Nissen-Ninomiya theorem, right, for lattice fermions, which tells that it's sort of difficult to put fermions in the lattice.
No,
There are,
it chiral fermions, yes.
so in the sense, it means that you probably do not like capture the kind of breaking effect in the well, anything related to that is like not seen in the lattice.
No, so okay. So first and foremost, there actually, what is interesting is there was a work done by Wilson and Ginsburg, which showed you could have that the breaking of chiral symmetry with Wilson fermions could be arranged in such a way that the breaking was, I don't want to use the word soft, but you could control it. But it made the theory very non-local. So if you gave up locality that you demand that, then you could actually have a chiral formulation. And today there are two ways of realizing it. One is called domain wall, and one is called overlap fermion. Okay, so you could actually put chiral fermion and get rid of the order A hard breaking of chiral symmetry, which is there in Wilson formulation.
Yes, so I know there are ways to sort of
Right.
overcome. So what do you do? What my question was, what do you
Your
do
group.
with this?
Huh?
Your group, which
How you
We are using Wilson fermions.
Yes.
And the one of the things which I did not talk about, which is the chromo EDM operator. We have problems because we are leaving an order A breaking of chiral symmetry, and that is creating, again, systematic effects which we need to understand.
I was just curious.
Because most of the things like the spectrum, you take the limit A going to 0, the chiral symmetry comes in as a dimension 5 operator, which is the Wilson term which you put into the action. And in the limit A going to 0, that vanishes. So you recover chiral symmetry in the continuum. Okay, so you extrapolate the results, and that's part of your discretization errors. But in the case of certain operators, what happens is if you have breaking of chiral symmetry. So take, for example, the quark chromo or even the Weinberg operator 3-gluon, GGG. That's dimension 6. It starts mixing with low dimension operators. And in addition, you get things mixing with operators which shouldn't mix with in the continuum, but mixes on the lattice because you have exactly the problem of chiral symmetry breaking, which with that dimension 5 operator. And so you have to deal with that much larger space of operators which mix and isolate the effect of all these spurious operators. So it just gets more complicated. See, I have to give you some optimistic thing. I've been doing Lattice QCD since it started. I mean, I started in 1980, which was pretty soon, 2 years or so after the thing. And it's taken 45 years for where today Lattice results for many quantities are the best there are. So, and we grew up with this enthusiasm, oh, we'll solve QCD in 10 years. And it's taken 45, but at least I can say in my lifetime, I've seen a thing which is actually now having an impact on phenomenology. I mean, G-2 calculation, everybody says, look, the only way we can now resolve it is through lattice. So it's yes, we haven't solved everything, but, and many of these calculations which are sensitive to this chiral symmetry will eventually be done using domain wall fermions or overlap fermions. which are more expensive, but we know how to do them.
There are no further questions. Let's try it again.
Sorry, this was not as planned, but
It's all good.
I have to come back and teach the field theory class, prepare notes which are sufficiently clean and clear.
Yeah. So we should go for lunch.
Yes,
Probably
I'm
starving, yeah.
Yes.
I think it's fine.
So, we try to have like
Yeah.
a working lunch because we want to ask about a few questions.
Yes.
So here's my student.
Yeah, sure, yeah.